we draw this introductory course in applied probability and statistics to a close by going back to a fairly comprehensive summary of what it is that we've done here in IE 6200. And in this particular approach, we've broken apart the course topics into really three bubbles of probability models and analysis as our first one, and then a very large and really at the heart of the course segment in statistical inference. And then we concluded with two modules with a couple of different applications that will pave the way for you on follow-on courses. In the probabilistic models and analysis block of material, we took a look at first just models of independent events, starting with the notion of Bernoulli and Poisson events, and that led us to a whole bunch of different models for discrete random variables, including the binomial model, the geometric model, the negative geometric model, and the Poisson model, and we had about 6 different models that we took a look at for these discrete random variables. And those tended to be of the counting sort, but they could be modified and used for other kinds of things as well, but for discrete random variables. And then we took a look at a whole variety of then models for continuous data that formed the basis for a lot of the things we did in statistical inference. And that perhaps most important one being the normal model that itself originates so much out of when something is a linear combination of something else, so a sum of a bunch of other random variables. So for instance, the sample mean is equal to the sum of a series of observations, and when that happens before the observations have been taken, then the sample mean is a random variable itself. Likewise, there's the log normal model that arises out of, rather than a sum, a product of random variables, and those might be raised to a different constant, different exponent, different power. And then we briefly talked about extreme models, really made more reference to them than did anything with them, and just to let you have some sense that they're out there, that for instance y being the max of a bunch of observations. That'd be one example of an extreme model. The Gumbel is one of those. We did spend some time talking about the exponential model. Exponential. And remember, that was quite useful for time between events, inter-arrival time, and then the Weibel is another one of these that's sometimes useful for time between events. It's also commonly used in, for instance, fatigue models, fatigue lives. And of course there are many other models that are out there for us, but those are some of the primary continuous ones that we took a look at. And then as we moved to what to do with those models, where would we apply them, then we turned to the analysis segment. And here in general we might think about y being some function of a variety of different random variables. We'll call it xi. It might be just x1 random variable, but it might be a multi-random variables there. So many of them, for instance, possibly. And many of the situations there then that we're working with are going to be that given we have, say, the cumulative distribution for x and this function that relates y and g, then question is, well, what's the CDF or the PDF, either way, of the function of this y, in which case that's a derived distribution. Right? Or maybe we have the marginals of both x and y, and we ask the question, what's the function that represents the relationship between those two? And we actually, in some sense, will see that later on when we come back to the regression models. Right? Now, another whole class of work that we did This could fit in the analysis segment if you wanted to, but is this whole notion of expected value. Where here, for instance, we defined the mean of this function y, the expected value of y. And if we had the PDF, the distribution marginal for y, then we could just find the weighted value, find for all the different values of y, weight those possible ones, and that's what's really going on inside this interval. Chose to represent this in the continuous case here. If instead we actually have our function g and the marginal for x, we can do this equivalently over in the x domain. But note that except for the linear case, it is not true that we just simply take this function and evaluate it at the mean value of the independent random variable. That equality does work if, but only if, it's a linear operation here. Right? And then of course the other thing that we're interested in very oftentimes is the variance of y. And remember, variance then is the squared deviations away from the mean. And so often the easier way to look at that x is not a part of that expression here, is that that's the expected value of y squared minus the square of the expected value if you're doing computations. And sometimes when you're doing closed form work by hand, it's a easier one to work with. So let's go back and take a look at one of these special cases, and that is that g is a linear function. And so we'll let y be equal to the sum of two random variables that have a constant in front of them, a1 x1 plus a2 x2. Right, and then the expected value of y in that case will be just a1 times mu1 plus a2 times mu2, where mu sub 1 is the mean or expected value of x1, right? And because the expected value operator is a linear operator and we have a linear function, we can do this swapping out this additive function and associative and commutative as well. Works quite well. Right? And then when we want the variance of y, things get a little trickier here. Right, because in that case now we've got a1 squared, the constant gets squared, plus the variance of the first random variable, and then a2 squared, variance of the second one. Right, so that would be just plugging in the variances for x1 and x2, squaring a1 and a2, the constant in front. But we also need that covariance term, and it turns out to be 2 times the covariance of x1 and x2, where recall that the covariance of x1 and x2 is equal to the expected value of x1 times x2 minus the expected value of x1 times the expected value of x2. Now, you could have related that to the correlation coefficient, right? And so we would have ended up here because of the constants that are out there, a1, a2 times correlation coefficient between x1 and x2 times sigma 1 times sigma 2, right? And we do have to get somehow the a1 and a2 term in there, and given the way actually I wrote this, really that should have been right in there. Right, now things can simplify down a little bit under special cases, if x1 and x2 are independent, then the covariance is going to be 0. So that term goes away, right? And further, if x1 and x2 are independent and identically distributed, and that distribution is normal, so IID, independent, identically distributed, then our random variable y is also normal, right? And it'll have mean of a times mu1 plus a2 times mu2, and its variance then is simplified down. Doesn't have the covariance term, in other words. Makes life a lot easier. Right? And this will turn out to be very important for us when we're looking at sampling distributions and inference. Right, now, the last thing that I'll summarize, but not necessarily last in the order of how we did things. Indeed, it was, in some ways, one of the first things we did was talk about composite events and probability trees, the probability theorems, such as total probability, and also the basic rules of probability about properties of distributions. Probability has to be between 0 and 1, and those sorts of things, and application of Bayes' theorem, conditional probability, joint probability is all somewhat back up in here as well.